are supposed to cover 4 today, but I think we were already ahead. So I wanted to ask you before I move on to the next lecture. So, any questions on this? So, if you remember, I just want to spend maybe a few minutes trying to recap. There are so many different topics we were looking at. One was, if you remember, optimality, right? And we talked about finite horizon and infinite time horizon. So we want to look at it. And then we also talked about Q-learning as part of the machine learning side of it for linear systems. Because we are going to repeat that every chapter when we bring some other things. And we also talked about neural networks if it is for nonlinear systems, right? And then we also talked about the issue of network control systems. What happens when you don't have a network and you do have a network? So you guys need to realize that that's very clearly, it has to be in your mind. Okay? So I want to just pause here and ask for if you understand that, it's going to get more difficult. And did you guys, I don't know whether Dr. Vera gave you the code. I was planning if he comes here, I wanted to ask him to share the code he shared already. So I suggest that, okay, since he's not here, maybe I'll say this. I suggest that if you have a laptop and you have access to MATLAB, this is a good way. I know tutorials is in the afternoon. I would suggest that you start running the code and you have the slides as well, right? And I think you may want to kind of look at it how the code was written. Of course, remember there's not many comments because this is not a commercial code that we develop, right, as a university. It's like if you're doing a research, you write a code that works, but you really never spend time on commenting and make it commercial. So that was not the goal, right? And the goal is for you to look at these code and see how it's, when you cover some slides, see how those equations are coming in and have you play with it. And when you're trying to play with it, I suggest you save the original one and then you rename the file, and then that way if you make changes to it, you don't get stuck, you always can go back. All right? So I encourage you to do that so that when you come to the tutorials, of course, not everything I can answer. Usually I don't get involved in the MATLAB programming. And so only thing is you want to see whether you get similar results. And second, how many of you have access to the book that, which is what I listed here? Okay, so there's only one. I suggest that each of you should have an access. Share, Sarah shared. So what is the PDF? Yeah. So, but I don't see anybody raising their hand. Okay. Right. Now there is a difference, right? In the slides, I don't put all that information. That's why I asked you. But if it is, and if you read the book, there are a lot more stuff in there. That's why I think it is better. So you will see there are things that were there, not on the slides, and sometimes that would help you. And why I suggested is because sometimes when you are looking at the MATLAB code, you remember I didn't go through in details all the math equations, but I think what I wanted to do is the next few minutes, I wanted to cover the Q-learning one more time. And I think Q-learning for linear and the other one non-linear. Every part of the slides have that. And you know why I'm doing that? Because there are so many different things, many of you may not have the background. And now, just like she said, that's where the jobs are. If you remember, I keep saying that machine learning and all, that's where it is for control. And not for control, pretty much everybody. Okay? So the traditional control stuff and all is gone now. You need to have that background, but very little that you will find because these new stuff essentially have the benefits. That's why you've been attending and you saw that what's going on right now, right? So it's important that you should have that background, the traditional one, but that goes without saying. But you also need to have what's happened, and whatever I'm covering is over 10 years old, more than 10 years old. The book has come out in 2016. Okay, that's about close to 10 years. But the work has been done 5-6 years prior to that. You see? So, and so that's how it takes. And industry takes a while for that to come out. So there's a lot of data that I skipped, but you will see that we talked about a little bit, and I'll show you how we are using the data and all that inside. So this is, in a way, this is a way to do data analytics as well. That's what the controller is doing, implicitly. Okay? So, and I think since we didn't have time, at least I didn't know, so we kind of went fast. But remember, that's why I said look at the book, because we are not going through equation by equation. The book probably explains a little better. And it cites some papers of us. You may want to grab the papers if you don't have the understanding, and the papers might give you a little more detail. You see? Okay? So that's what I wanted to tell you, because you remember we talked about Q-learning, we talked about neural network, but then we also talked about deterministic systems. Then we said, okay, whenever we have the network in there, it becomes stochastic. And we skipped all the basics of like how you apply those expectations and all, right? And you know, remember I asked you the Monte Carlo. Today also we'll see, you know, it's mostly averaging aspects. You run the same program multiple times. Every time you run it, it will pick up a different set of initial conditions, and you average those results out. That's how we do in stochastic. And this is typically done in the industry. You see, we normally don't run one time and just stop it. So these are the things that you've got to keep in mind. You know, not everything we kind of cover here, okay? All right, so any questions now? Let me ask you. It does assume that or no? Right. I think, you remember we talked this about it, so the time delay, essentially we assume it's bounded by a d-bar. And if you look at the model, to incorporate those delays, there's an expansion that goes there in the B's, right? That expansion goes all the way to u of k minus d-bar. That d-bar is the delay, right? So you could go more than one sampling interval, but as you know that there is a problem, as I mentioned, when there is a delay, that means that the system is an open loop. Okay? But you know, there is the control called event triggered control. There the delays can be more than a sampling interval. So it is possible to have a delay more than a sampling interval. Okay? So now there are some additional things you got to remember if you have that kind of a situation. The open loop system has to be stable within that time when the system is running open loop. Remember that. You see? Because if the open loop system becomes unstable, there's nothing you can do. Okay? So I don't know how many of you have taken a course on nonlinear control. Okay, so I'll ask you this because that relates directly what she's saying. Okay, did you guys study what we call finite escape time? Have you heard of that, what it means? So finite escape time is, if a nonlinear system, if you apply even a bounded input, for example, the system states can go to infinity in a finite time. Okay? So many times when we deal with nonlinear systems, we assume that the system doesn't have that property. You see? And why is this related to this, relevant to this discussion? Because if a system has that property, then if the system is running open loop, right? And in the network control system, what happens is there's a whole signal. So since the packets get dropped, what they do is just like in the digital control, they maintain the previous value of the control input rather than making the control input equal to 0. There are two ways you can do. One is the control input. Until you wait for the next one, you can make it 0, or you hold the same control input that you have before. Okay, so that's a bounded control input. So if you are applying a bounded control input, and if your system has a finite escape time, and you assume that the D bar, the delay is more than a sampling interval, the system is running open loop. And it's possible that the states already go to infinity. You see? So in most cases, we assume that the system doesn't have a finite escape time, or in other words, if you look at, there's another book that we wrote on event triggered control. Okay, we were the first ones actually looking at it after the paper was published in event triggered control in 2009. Okay, we were doing in the adaptive side of it. So one of the things they assume is the system is input to state stable. And that assumption is very critical. What it says is during that, the traditional nonlinear guys don't prove what happens within that event triggered interval. So what is event triggered? I don't know how many of you know. Remember I mentioned there the goal was to stretch the sampling interval. It becomes aperiodic. Remember the sampling interval traditionally is periodic. But I already told you when you have a network control system, when you are exchanging the state information as well as the control inputs, the network bandwidth is limited, so it can get congested, right? And therefore, you really want the interval to be stretched, the sampling interval. And by doing that, you are not really transmitting at every sampling interval, right? And so, but then you have these issues like what she said. Okay? So, in the event triggered control, basically you stretch that sampling interval and it's aperiodic. And you only sample when you need it. And when do you need it? When the system is about to become unstable. So, the traditional nonlinear control guys, where they assume the dynamics are known, they basically say that the system is input to state stable. So the same idea, input to state stable means when you are applying that, in that case, when you are applying the input, the system state has to be stable when the system is not closed loop. You see? So those assumptions you have to have it. If you look at my work on event triggered control, I have two cases in the Lyapunov proof. One is at the sampling interval and within the sampling interval. So, the assumption that, coming back to your question, that the D bar less than a sampling interval is not needed, but it's needed in some cases because of that issue. You are running the system open loop and you want to make sure the system is stable. You see what I'm saying? So, if the open loop system is not input to state stable, or if it has a finite escape time, then you can't do anything. This is a property of the physical system, nothing to do with the control. Okay? Any other questions?
Sir, your implementation of the control requires that expected values of these all are expected.
The history, yeah, that's right. That's what I was about to say. Yeah, that's right.
So when you are implementing that one, you are keeping all the previous.
That is in the memory. That is exactly the data science people are right now doing. Data analytics. Yeah. So there is some history, and I'm going to go over quickly since we are already ahead. And then so there is some history when we were showing that Bellman error convergence, and so I built a system by using the history of those errors, the temporal difference errors. So I do keep some in the memory. That is correct. Yeah, memory. And the same thing, remember, we also have an augmented state vector. The same thing, right? Yeah, so in the augmented state vector, you are keeping the previous inputs, the z of k. So not only the current values, but you can. But how many you keep it is up to you, based on the system.
There should be some limit will come.
That is correct. The memory and all that. That is correct. And it also varies with the system. not every system you may need a significant number of previous values. That is correct.
So is there any relation?
I think we have not actually. Yeah, we never really spent time there. We try because usually the students they rush to finish it off always, right? So we never really gone into like how many you have. But I think probably it's very difficult to come up with a relationship. So the only thing you have to do is mostly trial and error. Yeah.
That one thing. Second thing, sir, you are talking about that suboptimal.
Yeah.
So you are doing that one and you are fixing it here.
Right, that is correct.
But sir, I don't remember, sir, but in that procedure, there should come something like covariance or something should come, but matrix covariance should appear when I explain it that. Because in that time you are giving
Right. So, no, there is covariance, that is initial value of P naught. There is a covariance matrix which was, because you remember you need to have an initial value to start with. That is basically, those are the, I didn't even talk about that, but that's where you need to have that. Right. No, it is there. So the initial value would become like in a stochastic Kalman filter, you have the covariance and all. Yeah. And you know, the reason we don't talk about it, it becomes part of the system, whereas in a traditional stochastic optimal control, they bring it out because of the noise that goes in. Because here I did not cover the part, the stochastic in my case from the system side, but not from the noise or the, remember I mentioned that you could have that too, then you will have to define the covariance of the noise and stuff. Oh yeah, sure. Yeah. I think those you can't skip. Any other questions? So, you know, Professor was asking this a good question, how many past values you look at. So we haven't really spent time on, because we know that it varies with the system. You know, some systems which change fast, you may have to keep longer, and the ones that are slow, you may not need that many values, okay? But beyond that, you know, because memory is cheap. Even the computations now are getting cheaper now, you know? So, but you have to have some memory, okay? And I'll show you, I think those are good. So, any other questions before I can kind of point out where things are? So then we'll go into the new chapter. Any questions beyond these? So, if you look at it again, we talked about it, right? If you have finite horizon, you have a terminal constraint, which is non-zero. If it is infinite horizon, the terminal constraint will become zero. We talked about that, okay? And either way, if it's a linear system, we get Riccati equation for finite time. And that's a time varying. The optimal gain is time varying. If it's infinite horizon, the Riccati equation for a linear system becomes what? Algebraic Riccati equation. They become constants, right? Remember that. It becomes algebraic. And the Kalman gain or the gain matrix becomes constant. Okay, don't forget that, okay? And if you take the same analogy into the nonlinear domain, the Riccati equation becomes HAB equation. So, for infinite horizon, the HAB equation is not explicit function of time. Explicit function of time, remember that. Now, if it is finite horizon, then you should have a time t. Then you will have an extra time t. So when you do that, the value function that we talk about also will have an explicit function of time. So V is x of t, comma t, because that's also varying with respect to time. Now the only reason we don't deal with this for tracking, I didn't talk about tracking, but the reason we don't deal with that is because in function approximation, when you're using neural networks for instance, you have a problem because you have to have it on a compact set. And so when time is infinity, it doesn't stay on the compact set. So when you have a time-dependent trajectory, typically a trajectory tracking problem is explicitly a function of time. And so there's a lot of discussion, even though simulations work, but mathematically it is not correct to have a tracking. Here is regulation, but you can do the same thing on tracking. And if you do that, then you have the time, and therefore neural network approximation mathematically is not correct, although it works pretty good. Whereas for finite horizon, the actual activation functions will be an explicit function of time. I'm going to show you that. Don't pay attention to that. And that's okay, because they're finite, since it's a finite time, n is finite. Okay? So it is okay to have that on a compact set. But for infinite horizon, this is a problem. So normally, so there's a way to do it. We take the augmented system approach. That's also similar to what I presented. Okay, so the solution to HJB equation, you see that for finite horizon is time varying, and for infinite horizon it becomes a very standard, like algebraic Riccati equation. So here is again, I'm going to go back again, the LQR problem. The linear quadratic regulator problem, where you have this is a discrete time system. In this case, A and B are constant. It doesn't matter. A and B can be time varying. You get the same set of equations. So you see that we are defining an index. This term is called terminal constraint. You see that? And Sn is the terminal weighting matrix, which is up to the designer. You choose that. And here you see that the second term, I equal to k to n minus 1, this is what we call as, this term is called cost to go. The cost that goes within that n minus 1, 0 to n minus 1. And is always quadratic. You can pick non-quadratic functions. There are benefits to that. But for you guys right now, we are assuming this is quadratic, okay? So if it's quadratic, you see that there is a quadratic term in terms of state, and there is a quadratic term in terms of control input. Because you want to minimize the error in the state as well as the control input. That's what you normally try to do, right? So we talked about the derivations earlier. You end up in a Riccati equation because you have to solve for S of k. And that S of k goes in the control policy, and you see that kk is a function of S of k plus 1, a and b. So S of k plus 1 comes from the Riccati equation. Now, remember I said Riccati equation you solve backward in time. Now look at that, S of k is a function of S of k plus 1. So that's why you start with S of n. S of n is already given here. You see this? That is the terminal constraint. S of n is given, and then you come backwards. You normally solve backwards. S of n minus 1, S of n minus 2, and S of k, and then that's how you go backwards from the equation. And typically there's no closed form solution, so in Riccati you may find it under some conditions. So basically it's a challenge, okay? So it's a quadratic equation, and you can use numerical methods. But the problem here is it's a backward in time, as we talked about it, and you need basically what that is. So if it's a nonlinear system, so here f and g are nonlinear, smooth, then the same idea. You see, you have a performance index, and the performance index has a terminal state constraint, and the terminal constraint is given by the psi, plus this r is the cost to go. And you see that we use a recursive Bellman equation, v star xk. You see this v star is explicit function of k. Now remember, this is what I was talking about. Why is it explicit function of k? Because this is a finite horizon. For finite horizon, the value function becomes explicit function of time. Just like the Kalman gain becomes a time variable. Okay? And so now what you do is you write this as the k to k plus 1 and then k plus 1 to n minus 1. So that's what that is. So then the optimal control policy is basically not only requires G dynamics, but partial V star over partial x of k plus 1. Now typically V star is unknown. That's why we use a neural network. And that neural network is called what? What is that neural network that approximates the value function? Huh? That is called critique. Critique approximates the cost function. So there's another neural network we use to approximate the control input because you don't have the G. And that neural network is called what? Actor, because it creates an action, generates an action, which is a control policy. Okay? So you cannot forget that. So this is a discrete and here is the continuous. It's exactly analog to this. Okay, instead of summation you have an integral. Generally a JB equation, even though it's not time varying, doesn't have a closed form solution. Even if you know the dynamics, F and G, it's still very difficult to solve it. And so the idea was you want to use numerical methods to solve it. And that's what we call policy iteration or value iteration methods. So what they do, remember I said, you between any sampling interval, you hold the time, and then you are using the numerical methods to solve that JB equation. Okay? And again, that part is how many number of iterations you need is also not known. You see what I'm saying? So that's the problem that you need to remember that. And there are some references, I talked about it. So, but the goal was online and forward in time. I think that was the goal. Because otherwise we can implement backward in time optimal control in any of the applications. Okay, even if you know the system dynamics, even if you know that. So, this is the same thing that we talked in discrete time earlier I showed you. So, the Q-learning essentially relaxes that problem. That is, two things it relaxes. One is the backward in time, and what is the other thing it relaxes? A and B. A and B, that is correct. You don't require A and B. So, you cannot forget that. This is with or without the network. Remember that. We do this and then we are applying the same idea. So it's no big deal. Once you understand this, trying to go there. Remember, that's why I'm going through. Because we're going to talk about the quantization at 11 o'clock. So I want you to understand this reinforcement learning stuff. And I'll also show you some history stuff. Okay? So the way it works is you define a j of k plus 1 is equal to this. So you remember that Bellman equation is a recursive equation. So you use this equation, this v star of x of k plus 1. So the v star of x of k plus 1 is basically the j star of k plus 1, which comes out here. See that? That is what that is. Okay? So it's very critical. In some slides I have the details. So you see this part is basically that. Okay? So this equation becomes x qx plus u or u, that is this, plus, so this x of k plus 1 transpose s of k plus 1 times x of k plus 1. So that's what that is. So now what is x of k plus 1? X of k plus 1 is what? Is equal to a times x of k plus b times u of k. From the system dynamics. Right? That's what we did here. You see that? X of k plus 1. Oh, I think it doesn't change here. Okay, so that's basically, so what you do is, wherever there is x of k plus 1 transpose, you put a times x of k plus b times u of k transpose times s of k plus 1 multiplied by a times x of k plus b times u of k. Okay, so now what happens is, you see that there are terms with x of k, u of k, u of k. So you combine that and then you write it in the form of xk, uk, you pull it out. So xk, uk, and then you have a matrix. This matrix is g of k, and then you have x of k, u of k. And that's how we got that matrix. You see? It's no big deal. It's not difficult at all. Any questions here? Because we keep using that if it's a linear system, linear network control systems and so forth. Any questions, guys? It's not that hard. Okay? So once you have it, now look at that. You really need this term. We don't need this whole matrix, but you need that term. Inverse of that, multiply by that. And if you have that, that's your nothing but your kk. That's nothing but your gain. Now by doing this, and you forming this into an optimal adaptive control problem, because you don't know this matrix. Do we know this matrix if A and B are unknown? No. Because you see that there is A, there is a B. So we don't know this matrix. So we use what we call is Kronecker product. And you pull that, you make the matrix into a vector and you pull it out. And the rest X. So you write this as G bar, or in the book we put G bar transpose times some phi of whatever, okay, X comma U. Because you see that there is a xk, uk. So you pull it out and this basically is a long vector. So in consisting of that, and then you create it as an adaptive control problem and you estimate G hat at every instant of time, then you reconstruct that big G and then you compute the K. That's what you're doing. It's simple as that. Okay? So you compute that, you estimate it, so then this becomes adaptive control problem. And then you estimate at every time this, you see that? And then you multiply by the state and then you get the optimal control policy. Now remember this, for finite horizon, you also need to have the time, n minus k. N is the final time, k is the time, current time. So you're using the explicit time, and this is exactly what I said here. Okay? And that becomes an adaptive control problem. All right? Okay. So here is the inverse. Remember I said, here is the inverse times that. Okay? All right. So that's for linear systems. So that's called Q learning. So Q learning, you relax A and B, and it does work. Okay. So let's see here. Now, professor asked me the history, right? I'm going to show you this. So here, now you see this history stuff. So what you do, you have this n minus k minus 1, and you get that in the basis function, and you get this. So now look at that, the Bellman error, this is what I want to show you, is given by this expression q hat at k plus 1. So this term is the difference in the time with the cost to go. So therefore the error in reinforcement learning. So this is where you use adaptive dynamic programming. So that is where you're bringing in the adaptive dynamic programming, which is the reinforcement learning concepts into this. Okay? Now look at that. There is also a terminal constraint error because it's a finite horizon. Now look at the update law. This update law is basically try to solve it by minimizing the square of the Bellman error and the terminal constraint error. Okay? So now this is where the professor was asking. Look at that. You see this? That's the history. So I'm not formulating just this current value. I'm formulating that regression function as a history. Okay? And you need the history. The more values you have, the better is the convergence. We know that. But so you see that here, I went all the way to k minus 1 minus j, previous values. You see? Okay, so the same thing, in the cost to go, also you are trying to go to the previous values, k minus 1 minus j. And the number of previous values, typically you are stored in the memory. The number of values is up to the designer, how many you need, and it might vary with the system and time constant. There are so many different things. Okay? So once you do that, here is the update law. The challenge is how to come up with the update law. So all this with respect to, see this term is the Bellman error, but history. That big E, that's basically history. And you can see here, EK total is the Bellman error and the terminal constraint error. And then this term essentially has the history. So keep this in mind. And you see, professor, this is where you get the initial value. That's where you set the covariance, of that particular initial value of the system, whatever, right? So and then here is your control input. The actual control input, you take the G and you take this term inverse and this is hat. Hat stands for estimated value. Got it? And the goal would be is to drive the hat to the actual value. That's what the adaptive control does. Got it? And the proof shows that it's basically driving towards that. So when we prove it, we show a whole lot of stuff. We show that, first we show that the xk converges to 0 or a small, depending on what happens. And then g hat approaches g, and v hat approaches v, and u hat will approach u star, which is the optimum. That's a part of the proof. Any questions, guys, here? So this is the idea for linear and linear system, and so here are the proofs that normally we talk about. Okay, I didn't go through it, but you guys can go through it. And we talked about the output feedback as well last time. Okay, so now remember those update laws here, the adaptive observer, those are developed as part of the PhD work. And remember I said, and how do we derive those? Using Lyapunov. And those are, most of the students that work with me spend probably 9 months out of the 12 months doing that. And the 1 month in just getting the results. And 1 month is basically coming up with a solution. So most of the time we spent is on the proof. And that takes an enormous amount of time. Yeah. Now, is there any better way? No. So all people who are doing research, the main challenge is in the mathematical equations. That's why I told you simulations work, but we want to ensure that theoretically there is a guarantee. Yeah. Otherwise, in control theory, you can publish a paper. Okay, any questions, guys? So now, in the update laws, you see, the update laws are driven by the Bellman error. See, this is the output error for the observer. This is the Bellman error. Look at that. So that's what the Bellman error is, the measured quantity. So we are using that to drive the update law. So basically it's used to tune, and you learn, the G hat, and over time the G hat will be pushed to G. And when it gets pushed, the Bellman error keep going down to 0. Remember, that's what those plots are. Okay, so finite horizon, you have 2 errors, and we sum them up. The terminal constraint error and the actual Bellman error, remember that. Whereas in the case of infinite horizon, you only have a Bellman error, you don't have a terminal constraint error. That's all it is for Q-learning. The same idea works when you use neural networks. Okay, any questions here, guys? Any questions? So this is Q-learning without network. But when you have a network, it becomes A becomes AZK, B becomes BZK, and wherever you have those terms, you put the expected value. That's it. There's nothing different. The approach is identical. The expected value doesn't change anything. You only pick the covariance. Initial state, you pick some sort of a covariance or variance matrix because it's now getting into the stochastic domain. And you don't do it once in the simulation. Most of the time, you probably have to do 1,000 or 10,000 times. You repeat it, and then you average those values. So the states, errors, everything has to be averaged when you are plotting it. For ergodic behavior, that's called ergodic systems, ergodic behavior. Okay? So you guys heard of ergodic behavior? No? Oh, you guys might have heard. I'm positive, undergraduate. So as a homework, check it. It's called ergodic behavior, ERGODIC. I'm positive undergraduate, we all have one class. And it would come one of your math courses. And we all forget, unfortunately. And what's the best way to remember, guys? Do you know? What's the best way to remember? What's the best way? Huh? Learn is okay. But what is the best way? You will never forget. Let's say a lot of things we do, right? Riding a bike or driving a car, whatever. Why we won't forget? Practice. So you implement, if you apply this, you will never forget. So that's the problem with the Indian system that I was talking. We do a lot of exams, and after the exams, next you have a different set of courses. We do all that, but whatever happens in that class, we never use it again, right? And that's the problem. That's why we forget. I'm positive Indian system is strong in terms of those kind of things, fundamentals. But we never go back and apply. That's the problem. And that's why we learn a lot, but we never apply, and therefore goes up. Okay? Any other questions? All right. Now, I know some of you are master students, right? Maybe I'll take a little time about masters and PhD here. This is very critical. Let me show you this. Okay? I know all of us need money. Yeah. All of us need money. So, a lot of us just go with masters, don't care about PhD. But I'll give you in US, and I'm positive it's the same thing here, because I have students who came here, they have faculty in IISc Bangalore and some IITs, okay? So let me tell you what happens. So you have a master's, let's say MTech, right? You have a BTech, and this is MTech. And MTech takes about 2 years, right? Approximately. Somebody told me MTech students are getting less paid than BTech. That's not true. Actually, there is something wrong. If you don't ask more, there is seriously something wrong. Okay? That's not true. Okay? Let me give you in US, because I know the numbers. So BTech students get anywhere right now between $80,000 to $85,000. All right? So an MTech student, the starting pay for MS, we call MS here, we take MTech. So usually varies from 85 to 100K right now. Okay? So PhD usually takes between 3 to 4 years. If you have an MTech, it's much faster. A PhD gets 150K. This is the minimum. Okay? Now, BTech, this time is between 3 to 4 years, if you go through the same time. Now, do you think in 4 years you can make from 85,000 to 150K? Do you think it's possible? Impossible, unless you own your own company. You see this? Most people miss this. Most of them miss. The guy who wrote the book with me, he did PhD in 2.5 years. He's Chinese. So most of my students make 150. That other paper, the Travis, he got 145 in 2009. He's the director of a big robotics company, probably making millions. So why people don't go for PhD? India needs a lot of people. Yeah. So somebody told me MTech students get paid, that's all crap. I'm telling you right now. So if you don't negotiate, otherwise why would you want to go for a master's? So there is a problem. Of course, the salaries also vary with the skill set. Salaries vary with the skill set. So you got to have the skill. If you don't have the skill, naturally you can negotiate. Keep that in mind. Okay? So I'm not talking about these salaries, I'm not talking about Amazon or Microsoft. I have students, Google, Microsoft. They make even more. They're more than me, what they make. I have one guy in Amazon, he makes close to $500,000. He graduated in 2018. He did that cyber defense, I'll show you. Yeah, network control systems and cyber defense. So, I'm positive the same. It's not any different. So, just because you got an MTech, you shouldn't be expecting lower salary than a BTech. There's something wrong if you are saying to me, okay? So otherwise, why would you do PhD, right? Now, what are the other benefits for PhD? You don't get laid off. It's very rare that you get laid off. They don't hire that many PhDs. At the same time, they don't get laid off. So I'll give you my university statistics. Every year, we graduate about 800 undergraduate students across the campus, all different departments, okay? I would say about 250 masters. You know how many PhDs the university graduates a year? How many? Just guess. 40. You look at the comparison. Okay? So these are all the records. If you go to our department website, it shows you how much a PhD is making, everything. We usually use the low number, usually. Okay, so I'm just saying that a lot of times students don't realize it, and because nobody tells us at that time. But PhD means, when you're doing PhD or MTech, right, you guys get paid less, or some of you probably not, I don't know, GATE usually pays them some money, right? But how much they pay in a GATE? 9,000? Huh? 12,400. That's not much, right? A BTech guy who gets a job, he's making, let's say. So that's only a temporary for 2 years, remember that? That's what I'm trying to tell you. The same thing when somebody is doing PhD, the MTech person would be making more, right? But that's only a temporary. But the minute you get onto it, you will be far ahead. You will be far ahead than the person who just goes with the bachelor's. Okay? Yeah. But remember, while what I'm saying is true, PhD is not for everyone. Don't forget that. So in other words, you don't want to join a PhD if you don't have the inclination to work hard. And you probably have sleepless nights many times because things don't work in the mathematics. Remember I told you that so things won't work. And that's why I said today, out of 12 months, 9 months we spend time on the mathematics because it doesn't work always. Until you get up in the night and you find an answer. Okay? So that's where the no pains, no gain. Okay? Alright. This has nothing to do with machine learning, but right now, pretty much every company is expecting machine learning. Whatever I talk to you, the temporal difference error, all that is machine learning. We are applying this for control. And you see that data, I kind of skipped. All that comes in as part of that. How much data you pick, what type of data that. I just told you, you use the temporal difference error. But that's how you select that. Yeah. So, if there are chances, take a course on neural networks, maybe deep learning. Okay, those are useful. And I'm publishing quite a few papers now. We show a lot of methods now, which shows a significant improvement over all the other ones that they use in these big companies, that LLM, large language models and stuff. And none of them prove, we do prove that, so it's a positive side of it. So that's the benefit having all these mathematics and stuff. It's no fun. You think that it's no fun, but I will never leave that side of it. So the control has that very strong mathematical background. So you should be thankful to all the professors who teach you. Yeah, you go to computer science, they don't know crap about it. They use somebody else's work and they just write a software code. What did I tell you? Learn how to write software. That's needed. But once you do that, you are much more powerful than CS people because they don't know about the systems. They can't write just software because they need software for many systems. Remember that. They don't have that background. You guys have. Yeah. So learn how to do a little coding. Just not MATLAB, C code or C++ or Python. Now Python is wide. So many know Python. Most of you know. There's only one hand. Learn Python. Okay? Alright. Any other questions, guys? This is my 5-minute advice. This is fact. There's no bullshit in here. Yeah. Okay. So let's go back. So observer updates, we looked at it, and there are two flow charts, the same idea. This is the state feedback, this is the output feedback. And we do the same thing for nonlinear systems, and I showed you all that. So I'm going to skip here. Any questions here, guys? Any questions? This is what we covered yesterday, so I don't want to, I just went through quickly, but what I wanted to cover today is quantization. Okay? But we use the same concepts, Q-learning and neural networks. So we are going to go into the quantization. This is the quantization side of it. Okay? So every control system has this problem, quantization. Okay, I know we talked briefly when the first class. So why do we need to look at quantized systems? Why is that important? Where does this quantization problems come in? Even without the network control system. So let's say you are implementing a controller for a practical system. So where does the quantization problems come in?
So the controller is embedded, so it's the digital domain, but all actually system are...
All the stuff is in the continuous domain. So where is the quantization come in? Yeah.
ADC.
Huh?
ADC.
Yeah, ADC. So you always use either the A to D converter or D to A. Like she said, the controller is in discrete domain. The system runs in the continuous. So basically you need to have some sort of an interface, A to D, right? From the sensor to back to the controller, and D to A, convert the digital value into the continuous so that it has a hold basically between the sampling instant, it keeps the same value. That's all it is. So this problem occurs even without a network. So quantized means you have a finite word length on the A to D DTA, and you always have an error, just like you Taylor series expansion. Okay? So the quantization error typically is, if you don't use it properly, it can cause the system to become unstable. The same problem happens when you have a network, because the network is always operating in the digital. Okay, just like the controller. You see? And therefore the sensor value, if it gets transmitted through the network, gets quantized. And then the controller generates the digital value and it goes through the network. It's okay, the digital. But then when it goes to the actuator, it has to be converted back into continuous. So there is the quantization process. You see? And I'll show you today, because of quantization, there could be problems. In some cases, you can make the system unstable, even though you design the controller properly, okay? A lot of times we ignore that value, we just assume that there's no error between the quantized value and without the quantization, because none of us look at that, okay? So we will look at a little bit about it and see what will happen, okay? So that's what that is. So you see that this is network control, unknown because of that imperfections, and we have two cases, linear and non-linear case. Okay? So here is a block diagram. Now you can see that in the block diagram, there are two quantizers. One is basically quantizer from sensor to the controller. Like I said, the controller is a digital, and the controller sends in digital, and then you have another quantizer here, which actually needed to convert that into continuous. And that's here, the main reason is the communication network. Now there is an A to D DTA possibly, but the communication network also operates in digital. Remember that. And it uses quantization. Now look at the controller equation here, guys. So this XK, Q stands for quantized. So the controller uses the quantized value. A lot of times we basically miss that. We assume that it is not, that there is no error in quantization. You see what I'm trying to say? Whereas the controller is using the quantized value, not the value that the sensor provides. And that's what the difference is. And it causes problems. Okay, so here is a linear system. You have a network, and the controller uses the quantizer. So therefore, the UQ, you see, we used to say UK, but here it's showing as UQ. Yeah, the pen is, let's see if I can use this as a mouse. Yeah, still bad. Okay, all right. So quantization effect is inevitable in computer-based control. That's why I told you, even if you don't have a network, you're going to face this problem. Quantizer model plays a role in the control design. A lot of times we don't spend time in them. So there are quantizers called static quantizer. That's what normally we use. There the step size is fixed. Now I'm going to talk about a dynamic quantizer which was developed in early 2000. Okay, where the step size varies over time, and there are benefits for that. Okay, and I gave you some literature. You can see that dynamic quantizer originally was done by Leverzon. He's a faculty in Urbana-Champaign. Got his PhD from Yale. And so, as early as in 1990, they developed what they call static quantizer and how that linear system is stabilized with quantized state feedback. So, but dynamic quantizer was done with nonlinear control ideas, so they assume that the dynamics are known. So what I'm going to present is what happens you take it to the unknown case, when the dynamics are unknown. You understood that, right? That is the difference, okay? So here there is stability analysis but no control design. So here is the background, like you can see that you have the controller, UQ, so that's what I'm doing here. With unknown A and B, here is the terminal cost, here is the cost to go, and two quantizers, one for the system state and the other one for the control. Control inputs based on the quantized state, that is UQK is that KK times XKQ. Now remember all these chapters before, we used XK. So here we are now talking about a quantized value. So what I'm going to do is, I assume that the network has no losses, but I'm going to use the quantized value but no losses. Remember, these are different aspects. The packet losses and delays, we already talked about it. No, you can still have a stochastic because you can still add the noise, and you can still make it as stochastic. Otherwise, it becomes deterministic. Yeah, so in the book actually talks about that. Look at the book, it does talk about it. One of my students did the quantized system, but that was deterministic, whereas in the book we converted into stochastic. Because in the original work we did with the student, we assumed that the network is lossless, where we didn't have the delay and stuff. Whereas in the book we converted that into expected value, that is with loss. You can do both. Okay? Any questions here, guys? What about quantization? Okay, so it's 11 o'clock, we're going to stop, right? We have tea. Very good. Very important. So how many of you watched the match yesterday? Yeah, that's a big deal, right? There's more to celebrate, maybe that's the tea. All right, guys, we'll see you in 5 minutes. Okay, bye.